All right, so I'll go ahead and get started. So, coming up pretty soon, we've got, I guess, one more assignment that's going to go out, and it's to be implementing something called latent Dirichlet allocation, or LDA, on an architecture called a parameter server. So new architecture, somewhat new learning model. So how many people have studied LDA in the past? Really? Just only one? Okay. So the rest of you, this is all pretty new, okay? So, but you guys know directed graphical models, Bayes nets, D-separation, that kind of stuff, belief propagation. Is this ringing a bell? Is it like sort of reopening old wounds and sort of? All right, so I'm going to do like a kind of quick introduction to that kind of stuff, and then we'll go into LDA. So this is really supposed to be, I guess, review. This is stuff that's covered in 601. When exactly they cover it in 601 depends on the instructor, but hopefully by now. We're like way in November. So here's the canonical example of a directed graphical model. So we've got four random variables. Burglar, earthquake, alarm, and phone call. And what you're expected to model here is the world, is the situation in the world. So you've got this burglar alarm. Sometimes it's triggered by burglars, sometimes by an earthquake. I haven't been to California, but I hear that this is actually something that burglar alarms do. When there's an earthquake, a lot of burglar alarms go off. So probably those things are independent. So probably if your house is being burglared or being robbed, that doesn't increase or decrease the probability of an earthquake. Although if you go the other direction, it might be that the burglars kind of come out when there are earthquakes, or maybe they stay away. Maybe they just stand in doorways and don't go out and rob people. I don't know. But presumably these are independent. Okay. And the problem here is to basically understand kind of this causal model. It's not necessarily causal, but we're going to intuitively think of it as a causal model. Really, it's a probabilistic model. What this basically says is that the alarm only depends on the burglar and the earthquake. The phone call that you get from a neighbor only depends on whether your alarm is going off. Okay. So the arcs basically define the form of the probability distribution. These variables are all discrete. This is basically saying, here's a generative story. We decide whether the house is being robbed or not. We decide if there's an earthquake, so those are basically just binomials, true or false. Then we've got an alarm, and that's true or false depending on the values of whether there's a burglary or an earthquake. Okay, so so for each one of those things, the alarm is either true or false. Okay, so we basically have four binomials, one for each combination of Boolean variables here. Okay, and then finally we have two more binomials that basically, if the alarm's going off, what's the probability your neighbor calls you? If the alarm's not going off, what's the probability your neighbor calls you? Okay, so the generative model is we basically pick these things and then we pick the descendants and keep going until we've picked everything. Okay, so that's the generative model, but of course this defines a joint probability distribution. So we can compute lots of other things. So if I know I've got a phone call, I can figure out what's the probability my house is being robbed or that there's an earthquake. Or if I know that I got a phone call and I know there was an earthquake, I can figure out what's the probability that my house is being robbed. And one of the cool things about this is that this does some sort of intuitively obvious things natural things when you do that simulation. So if it's the case that when you get a phone call and you believe that with high probability there was an alarm, but you're not sure why, then you'll put some probability on burglar and some probability on earthquake. If you know that there's also an earthquake, maybe you look on Twitter or something like that, then that's sort of a sufficient reason for there being an alarm, and then the probability of there actually being a burglar in your house starts to go down. So you get kind of these interesting, plausible reasoning effects. And of course, we can see how you could do this. There's this generative story that gives you a joint probability. in the worst case, which isn't really that bad for this tiny model, you could basically just compute all the joint values, right? And solve questions, answer questions like, what's the probability that my house was just robbed, given that Twitter says there was an earthquake and my neighbor just called me? You can solve those sorts of problems just in a systematic way. But of course, the way we really do it in Bayes nets is we use these complicated message passing algorithms. So I'm not going to try and cover all these, but I'll just sort of remind you a little bit of kind of how it works. So the simplest one is called belief propagation. So if we're trying to figure out the probability of this variable x, they're basically, there's sort of two things we can look at. And the simple forms of these algorithms basically assume that this is not quite a tree. Basically, they assume there's only one path from every node to any other path. So that's called a polytree. So there's basically the information downstream. So, I have the alarm, and then, after some stages, I get some evidence the neighbor calls me, or, my phone buzzes, which indicates the neighbor called me, right? Or someone tells me, oh, I think I saw your phone buzz, so maybe that means the neighbor called you. So you can have a kind of indirect chain of evidence kind of going down. And of course, those things can have other causes as well. You might tell me the neighbor called me, but maybe you're just messing with me for some reason, right? Roommates do that sometimes. I don't know why. There's also evidence kind of upstream, so the things that are kind of potential causes of X, right? So there's whether there was a burglary or an earthquake, or whether California's overdue for an earthquake, or whether crime statistics are up, or so on and so forth. Okay. So there's this evidence above, which is sometimes called causal support, and then this evidence downstream. So evidence are the variables you know the values of, and then there's some set of variables you want to do inference over. So you want to find their posterior probability given that evidence. The algorithm gets a little bit complicated. Basically, the probability of X given all the evidence is a factor. It's a product of two different things. So one is the downstream evidence giving X. Okay, so the stuff down here given X, and also the probability of X given the upstream stuff. All right, so there's a constant of proportionality, which has to do with Bayes' rule, but basically it's proportional to the product of those two things, which kind of makes sense. And this is basically what gives us an algorithm. So the probability of X given the upstream probability basically kind of percolates through the graph. So you can break it down to something like this. You're marginalizing over the possible parent states for X. And then for each of those, you're trying to figure out the probability of that particular parent state given the upstream probability. So your inference tasks kind of percolate up the tree, and the evidence basically sort of percolates down the tree. Once you figure these things out, you can get distribution over X. And then for the evidential support, it kind of goes in the other direction. So the simple case is you only have to worry about things that are direct causes of X, right? So in that simple case, you get something kind of similar. You're looking at the product over all the direct causes of the marginalized value of that given X. So things sort of percolate in the opposite direction. So to figure out this based on the downstream evidential evidence, what you have to do is you have to solve these Y problems and then propagate that information up. But it's a little bit more complicated to do it in general, because actually whether X is true or not certainly depends on what evidence you have about Y, but it also depends on Z. All right, so this is this explaining away property. Think about this as earthquake and this is burglary, and in general there's some other things above that as well as below it, and then you get some evidence, you get some information about Y. Okay, so once you know that your neighbors called you, probably it's a burglary or an earthquake. It's probably not both. So the fact that you got that evidence couples those two things. They're no longer independent. So there'll be information that's kind of flowing from here to here. Okay, so that's sort of another sort of like complication in this model, but it's sort of what makes the model interesting. So this is kind of just a really quick scheme for what the what the process of belief propagation looks like and how information flows through these networks. This is kind of, I know, a quick review, but I just want to kind of put you in mind of that. So kind of the key things are when you're looking at the evidence for a node, you have to multiplicatively combine the evidence from upstream and downstream. And also, once you have some known common causes, then information sort of flows back and forth between those. Okay. So the top level belief propagation is kind of this recursive thing. It's not that important, but it'll be important for remembering sort of the general scheme for that will be important for understanding the LDA model. Okay, so when I talk about LDA, I used to just sort of put out the little pictures that were in the original LDA paper and expect people to understand. And then over the years, I found that a lot of people sort of misunderstand some basic things. So probably you're not one of those people, but just in case there's somebody like that in this room, I'm going to kind of back up and kind of go through the notation and the ideas pretty slowly. I'm going to start with naive Bayes, which we all know and understand, and describe that as a directed graphical model. So there's a generative story, and our graphical model kind of describes a generative model, a generative story. So the generative story is we pick a label, okay, and then we pick each word. So for every document, we pick a label, then we pick each word. So this is basically a bunch of random variables that are being instantiated in some order. We don't have binomials here, instead we have multinomials, so we've got a word for each x. But the picture's kind of the same as in the burglar example. The only thing we need is we need some way of describing these loops, which is traditionally done with these boxes called frames or plates. So this plate diagram shows that you have D copies of this, and then for each example, you have like ND copies of this. So you have ND words that are all generated according to this. And you know, usually in a graphical model, we sort of use the structure of the model to describe the kind of architecture of the generative story. But the parameters are kind of stored somewhere else. So the parameters that tell you what's the probability of picking y, there's a binomial for that if it's just two classes. The example I used in 601, these are 601 slides, there's a problem where you're trying to distinguish fake news from The Onion versus real news from The Economist, which is like a serious news source. So that's the classification problem, two classes here. And then for every x, there's a multinomial that tells you what the probability of each word is given y, so that's what naive Bayes looks like. So this is a reasonable way of describing it, but it leaves out a lot of stuff, like it leaves out how many classes there are. It leaves out interesting details like how we do the smoothing. So let's talk about smoothing for naive Bayes and how we can stick that kind of process in this sort of picture. Okay, so earlier this semester we looked at the problem of doing machine learning as optimization, and the kind of simple warm-up example I gave was finding the parameters of a multinomial, of a binomial. So in the binomial, you flip the coin n times, you get k heads. The map estimate is, or the MLE estimate is k over n. Or in this formulation, if I had alpha 1 heads and alpha 0 tails, then the probability of getting heads or tails on MLE is this. Okay, but often we add some smoothing. Okay, so there are different ways of writing the kind of usual ways we smoothing, but one simple way is to basically say, well, there's some number of imaginary heads, gamma 1, and some number of imaginary tails, gamma 2, gamma 0. And instead of just using the raw counts, I smooth them by adding in these imaginary numbers. So a typical thing might be you assume you imagine one head and one tail. So you add one on the top and two on the bottom. Okay, so that actually corresponds to a Bayesian reasoning scheme. Okay, so what you're doing when you're using this estimate is mathematically, I mean, it looks just like a hack, right? We're just putting in some imaginary data. But you can mathematically justify this as follows. you can say what I'm doing here is I'm choosing the most likely posterior value of that parameter, okay, given a particular distribution over theta, all right? So that distribution depends on how many imaginary examples you chose. So 5 and 5 basically means you chose, an equivalent number of heads and tails around 5, okay? So that gives you, without seeing any data, the most likely probability is about 50%. If you imagine, 2 tails and 8 heads, or 8 heads and 2 tails, it would give you a different probability, prior probability. And once you get the data, you're basically looking at the posterior probability of the parameter. Or if you like, you're maximizing the probability of the data given the parameter times the prior probability of the parameter. All right. So that's one way of justifying this for a binomial, this sort of smoothing. So we're basically treating the smoothing as a prior over the parameter value, which basically is kind of keeping it from very extreme values, right? So this is going to assign very, very low weights to values around 0 or 1, and that means we can't, we're not going to estimate 0 as a word probability if it's a word we've never seen in training. So that's nice. That makes our algorithms a little bit better behaved. And we can also write this as a directed graphical model. So here's the data that we observed, okay? And we also have some fixed parameters for our beta. So we've got some imagined numbers of heads and tails. These are our smoothing parameters. We know these and we know this, and then we have to estimate this, okay? So these blue things are what you know. The white things are things that you might want to do inference over, okay? So this is one type of inference. So here we're basically sort of trying to find not the distribution of these things, but the most likely probable value for them, okay? And I guess one thing this kind of emphasizes is when we're doing directed graphical models in 601, the form of the distribution associated with each of the nodes is very simple. So each thing depends on its neighbors or discrete values, and basically, each discrete value is chosen from a multinomial given the value of its parents. So it's a simple distribution. Of course, you could have a complicated distribution. So the way theta depends on gamma might be some horrible, hairy, horrendous mathematical expression, and it might be really hard to do this inference step. So just because the graph looks easy doesn't mean the inference is easy. So that's something else to kind of think about. So if my data is actually a certain number of tosses and there are some heads and some tails, we might write it like this. So we've got a set of coin flips, all right? So there's alpha 1 plus alpha 2 flips, right? And I'm using that to estimate theta. All right, so this is basically describing smoothing for a binomial as a directed graphical model. Does this kind of make sense to people? So there's a generative story. I pick my prior probability. I pick theta from that prior probability. Then I get a bunch of data, which informs me as to what the value of theta is. Okay. So the inference step is given what I know about these things. What are the likely values of theta? Okay. So this, of course, is not a case where the inference is hard. So this particular kind of distribution where essentially when you go from here to here, what you're essentially doing is adding pseudo data. So what this is basically doing is just telling you what flavor of pseudo data you're adding to your estimate for the parameter. That's called a conjugate distribution. So here the theta is the parameter for a binomial. So it's just the probability of a coin toss. And the conjugate for that is a beta distribution, like I showed you before. One of these guys. That's a beta distribution with various parameters. If theta is not a binomial but a multinomial, so say instead of flipping a coin, a certain number of times, I've got some distribution over words, right? And I'm drawing many words from that distribution. So then this distribution is a multinomial, not a binomial. It's many discrete outcomes, right? And the conjugate for multinomial is called a Dirichlet, right? It's got a fancy French name. You always capitalize it in deference to Mr. Dirichlet. What that prior looks like, again, it's like a beta. It basically has parameters that tell you how much data you've imagined. So here you have to have imagined data for each of the outcomes. So if they're 10,000 words, you have to have 10,000 sort of imaginary draws, which are the number of times you saw the word aardvark, the number of times you saw the word, Aronson, the number of times you saw the word so on and so forth up to Zybergy, okay? So, or if they're just like, this is like choosing a set of 3 classes, then you have to have 3 sets of imaginary numbers, pseudo counts for class 1, class 2, and class 3. So that's called a Dirichlet. And the most common form of the Dirichlet is you basically hallucinate the same number of examples for each class. That's called a symmetric Dirichlet. It doesn't make any of the classes more likely, so it starts off kind of uniform. So that's sort of the way you smooth multinomials. So now we can put all that stuff together with our naive Bayes model. Okay, so for naive Bayes, there are basically 2 things I might want to smooth. And also there's a number of classes, right? So let's say I've got k classes. This is my full model, all right? This 19 is the slide number. Don't be confused by that 19. This is how close we are to going home. Okay, so what do we do? First, we have this Dirichlet prior. So from that prior, we're going to just draw a multinomial, okay? So we're going to choose some multinomial from that prior, okay? Then I'm also going to choose my, my word distributions, okay? So I've got, again, another Dirichlet beta, okay? And from that, I'm going to draw for every class a multinomial over words, okay? So this is a multinomial over the vocabulary, lots and lots of outcomes, right? And there's k of these boxes, k is the number of classes we have, okay? And then for every document, I'm going to generate this document using this model. So first, I pick the class label, okay? And then I pick the word. So the word depends on 2 things, obviously the class label, but also the multinomial associated with that class label, okay? So it's got 2 parents, the class label and the multinomial, right? In the data, I know one of these. I know the class label. I don't know what this one is, and I don't know what this one is, okay? So this is a model of naive Bayes. We're sort of explicitly making clear all our little Bayesian assumptions. We've talked about how we're going to do the smoothing here and the smoothing there. So just putting in different known values for alpha and beta change the smoothing parameters. So there's a very clean little description of the algorithm. And it also tells us what we're trying to do. What we're trying to do is we're trying to infer a value for pi, which is the class probabilities, and also for gamma, the multinomials question.
What's the analog of theta here? The theta that we saw in the previous slide?
Where's theta?
In the previous slide for the
Here?
Yeah.
Okay, so this is a different example. This is choosing the parameters of a binomial. All right, so we don't have any binomials in this. We basically have 2 multinomials. One multinomial is up here. It's over the classes, but they're k classes, not 2, okay? So this is a multinomial with 2 outcomes, or with k outcomes, right? And this is the smoothing for that. And the evidence we get is basically what, how many classes do we get of each, how many documents do we have in each class, right? And the other one, well, I guess the other k are down here, okay? We also have k multinomials, 1 for each class. And these have the same smoothing parameters. So they're all drawn from the same Dirichlet, but they're different, yeah.
But if we have a lot of data,
Why do we need smoothing?
If we have a lot of data, why do smoothing?
So it might be that the parameters for this basically give you very, very little smoothing. In many cases in practice, people don't smooth the classes. If you're in a situation where there are lots and lots of classes, or maybe you're assuming some sort of hierarchical distribution over the classes. You might actually want to do some smoothing over classes, just so you don't score really badly when you see an unknown class. So when I move this up to LDA, we're going to definitely want to do smoothing. Okay, everywhere we have to do smoothing. So here, when we're looking at a multinomial over the number of words, then we definitely need smoothing because there are lots of rare words, and we could very well see a word that only occurs with one class, right? And then if I go to a test document, then all the classes that it never occurred with will get a score of 0, right? If I see a word in the test that wasn't in the training, then it would just sort of say that's 0. Okay. And when I take logs, which I'm always going to do, I'll get like an overflow. So that's why we want to do the smoothing. Okay. So how we want to do this smoothing, I mean, this is like describing a pretty simple way of doing it, but this is one model for the smoothing. All right. So we can also use the same picture to describe other algorithms. So one kind of interesting algorithm is basically unsupervised naive Bayes or semi-supervised naive Bayes, where some of the documents are labeled with classes and others aren't. Or in the unsupervised case, nothing is labeled. Okay? So now again, I've got the same inference problem, but I don't know what the label of each class is. The generative story is exactly the same. I'm still assuming everything's generated the same way. I just have less information. Okay? So that changes what the inference task is. Okay? I need to find values of y. So I need to figure out what the label of each document is, or what the distribution of possible labels is, as well as this distribution over class labels and these multinomial distributions. Okay, so the most commonly used algorithm for this would be EM, but this is basically a description of the task as sort of an inference problem. These are what you know, right? The form of this distribution here is a Dirichlet and a multinomial, Dirichlet and a multinomial here. So it tells you what the form of the distribution is, and then it's kind of up to you to figure out what inference scheme you're going to use. This is basically sort of specifying the problem. Okay. So this is another reason why it's useful to have these kind of diagrams. So it's very easy to see, if you can control your clicker, it's very easy to see that this problem and this problem are related and how they're related. If you look at just the code for the algorithms, you might not see that. Okay, so this is all preamble. Okay, we know naive Bayes, right? I don't really need to give you yet another way to describe it. But this is the way that people in this kind of topic modeling community describe their models, in particular how LDA gets described. So LDA stands for latent Dirichlet allocation. So this is a paper that came out in like 2003. David Bly, I guess, was the first author. Andrew Ng and Michael Jordan were other authors. I was just saying how many times it was cited. This was 14,000, but this is a couple of years ago, actually. So it was up to 16,000 last time I looked. So it's an extremely influential paper. It's actually a really simple idea. So here's our unsupervised naive Bayes model. So they got 16,000 citations for changing it so it looks like this. Okay. Let's break down these significant differences. Okay. The basic difference here is where these boxes get drawn. All right, so this box has been kind of stretched up a little bit to cover the y, and this box has been stretched up to cover the pi. Okay, so that's your 16,000 citations, worldwide fame, job at Princeton, then Columbia. The basic difference here is here we've got one latent variable per document. Okay, so there's this y, an unknown class for the document. All the words are drawn from a multinomial determined by y. We've just got one of those per document. Here I've got one per word, okay? And then here I've got one class prior over the whole corpus. So I've got one unknown multinomial that determines the frequency of these labels. And here I basically have one of these for every document, okay? So this has a gazillion more parameters, basically, okay? So for every document, instead of having a class, there's an unknown distribution of classes. And for every word, there's a potentially different class associated with that word, okay? So that's the basic idea. Actually, let me skip ahead a little bit to something that I don't have this next, but this is really the next thing to look at. So here's a view of what the document is according to LDA. So they're basically here. There are 4 classes indicated by these different colors, and then the black things. I guess we have low confidence as to what class they're in. But this is what LDA thinks this document is about. Okay, it thinks that this word is from education. I'm an educator, what can I say? School, about education, school, taught, these are all about education. Budgets is this green stuff, so foundation, million, research, well, that doesn't have much to do with money, but provide, receive, that all makes sense, okay? And then this is about children, so social, traditional, opportunity, future, so on and so forth. So these are the names of these latent classes that we're inventing. So David Bly came up with these names. The names aren't by themselves meaningful, but the key thing is that each document is there's a potentially different class for every word. And this document is sort of coherent. It's mostly about budgets and arts and children and education. All right, there might be lots of other classes, but they're about other things. And we want to look at so this is actually, we can see at least 27 different models here. So this document is mostly about these 4 topics, okay? And if we look to ask what these topics were about, so given topic 13, which David Bly labeled as arts, the most frequent words, if you look at the multinomial associated with that topic, are new, film, show, music, movie, play, a musical, best, actor, so on and so forth. For budgets, million, tax program budget, billion, federal, so on and so forth. For children, women, people, child, years, families, work, welfare, percent, so on. Education, school, students. Where's William? I'm not even on the list. All right. So this is the basic idea. And this is the model. This is the differenomials. The other important change was to change the variable. So we're going to go forward. So now this is theta. This is this multinomial for a document. So I'm going to try and use theta sub d. So you remember it has to do with a document. This is the latent class associated with the ith word in document D. That's the actual ith word in document D. Z is sort of the hidden class, theta is the hidden distribution, and gamma k is the kth multinomial. All right, so that's just the notation we're going to use going forward, and because it's David Bly's notation and everybody uses it. So this is a big inference problem. We basically have to come up with some latent classification of every word in a document. So this is really, it's a different kind of clustering problem. Really what we're doing is we're clustering the words, okay, not the documents. So just to motivate why this model makes sense, so in Bly's paper, they start with this assumption, which they call the bag of words assumption. So generally when you're doing modeling of a corpus, you make 2 assumptions. One assumption you make is that the documents are all drawn from some static distribution. And the next assumption you make is that within a document, the words are all drawn from a static distribution. So the order of the words doesn't matter. All right? So that's the bag of words assumption, and the documents are IID assumption. So that basically means your model has to look something like this. For every document, you generate some distribution for the words. Okay, the words are all IID, so there has to be a distribution. Okay, and then each word is drawn from that distribution. Okay, so this is basically the skeleton of the model that we have here. Okay, now the next thing to do is figure out what's the form of these distributions. So we know we've got this big box. All right, we know there's a theta inside every box because the words are IID. That has to be the case. And the words are all drawn somehow from that distribution, but there might be some other steps in the middle. Okay, So Bly, Ing, and Jordan basically said, well, let's just take this and realize it as follows. Okay, so this is a multinomial over classes, and then for each class we generate a word. So this is their way of taking that model, and this is sort of why they moved those boxes the way they did. Question? So the classes are, so the way to think of those is as topics, okay? So the classes are groups of words that tend to kind of co-occur in the same documents, right? So, in this picture right here, this group of words tends to co-occur, all right? So they're just words that are sort of thematic, sets of words that are thematic. Outcomes, all right, and based on that index, I choose a multinomial, and then I choose a word from the, if I chose, 14 here, I choose a word from the 14th multinomial, all right? So in this particular case, there's a document, most of the words that are chosen are from one of these 4 topics. So this distribution here is picking mostly whatever it was, 13, 27, and so on, all right? And then when I'm picking words from these, all right? So the most likely words are for topic 13 are things like opera and musical and actress, right? The ones for topic 27 are mostly parents and children and women and so on. Okay, so that's the idea. So these latent classes are called topics. There's a fixed number of topics, which is basically sort of the number of clusters you want to assign the words into. And every topic is associated with a multinomial over words. So that's the big estimation problem. So SVM works pretty well. So here are a couple of examples. So what they did here is what you do is you take a bunch of documents and you infer what this distribution is. Or if you like, you're inferring what these latent topics are for each word. And then you're modeling a document basically by the portion of topics that each document has. So this document, it's maybe 20% this, 30% this, 15% this, 10% education, the rest sort of scattered around everything else. So what we're going to do is we're going to use those mixing coefficients, basically the proportion of data you use, and we're going to use those as features. So this is with 50 document topics. So we've broken the world into 50 topics. So every document now gets represented not as a bag of words, but as a distribution over topics. So it's a dense space. We've got 50 topic probabilities. And we can do machine learning with that, okay? So this is using support vector machines using this particular representation. So we basically do the unsupervised learning first, and this is support vector machine with word features. This is with the topic features, okay? Yeah, what's different? Oh, these are just 2 different classification problems, okay? But it's a very sort of common situation. Basically, if you don't have a lot of training data, then this kind of unsupervised learning will give you a sort of a useful representation that you could do learning on top of. Okay, so this is semantically what LDA is. Okay, so are there questions? The next thing I'm going to talk about is how to learn it, okay? Yeah. So this is supervised learning, but you do unsupervised learning as pre-processing, okay? So you use LDA to figure out what the unknown topics are for each word. Then each document, instead of representing it as just a bag of words, you represent it as a vector, where each component is the fraction of each component is the fraction of words in that topic. Okay. So you've gone from a very sparse high-dimensional space to a much lower dimensional, denser space. Okay. So it's really a lot like doing something like SVD on the data and then doing supervised learning on top of that. Okay, so let's move on. So there are a couple of different ways of doing LDA. So a variational EM, I'm not going to talk about. Gibbs sampling is a fairly simple and widely used technique. That's what you'll be doing in your homework assignment. So today I'm going to kind of go through this. There are lots of places to read about collapsed Gibbs sampling, but why not get it from me, right? Okay, so this is a sampling algorithm, but it's also a learning algorithm, and this is kind of a little bit hard to get your head around. But yeah, the basic idea is once we've described a learning problem, like say naive Bayes or LDA as a graphical model, then learning basically becomes a question of figuring out what the unknown parameters are. So one way we can figure out what the unknown parameters are is by basically sampling from them. So here's the general idea behind Gibbs sampling. So I've got some set of variables that are all connected. So I've got variables, I guess, 1 through n here. And I basically go around a loop. So first I sample x1, given the current values of the other n minus 1 variables. Then I sample x2, giving the current values of those other n variables, and then so on and so forth, right? So I basically sample each one. At each point, I have to sample a variable given the current values of all the other variables in the model, okay? So I basically keep doing that, and at some point, in many cases, this will converge. So these x's will all be basically taken from a static distribution. They're not going to change very much. At that point, you can stop if you figure it out that you're allowed to stop. And you will have a sample from this joint distribution of these xn's. All right. So the key thing you have to be able to do here is to estimate the distribution of one latent variable given the other latent variables and all the observed variables. All right. Okay. That's kind of abstract. Let's break it down. Here's my model. So let's see what happens here. So in this model, I choose a class, one of these two classes, okay, class 1, class 2, all right? So I choose a class, okay, so yeah, so there's a distribution over classes. So it looks like it's about 50-50, but I've got some smoothing parameter for that. And then once I've chosen that distribution over classes, I repeat the following thing many times. I choose a latent class variable, and then I choose x and y given that class variable. So, maybe x and y are basically drawn from some Gaussian or something like that here. Okay. So this is my model. Here's like sort of a data set that might be large enough to kind of actually work with, just for fun. That doesn't fit on a slide, so we'll just have 2 examples here, 2 points here, 1 and 2. Okay. So we start out, let's assume I know basically the parameters of those Gaussians. So I know the probability of x given z and y given z. All right. So I know what these Gaussians are. I basically just have to like sort of figure out which, for my the 2 points I actually have, what cluster were they drawn from, all right? And then from that, what's the distribution over clusters, okay? That'd be totally reasonable to do with these 20. It's probably kind of silly to do it with 2, but I want to kind of have things fit on the slide. All right, so this is a graphical model, right? So this is the prior for that. This determines these guys, and this determines these guys, right? So this is the evidence. This is what we can see. This is what we can't see. All right, so here's Gibbs sampling. All right, what I'm going to do is I'll initialize all these hidden variables, the ones I can't see randomly. All right, then I'll draw z1 given the probability of z given basically everything else, okay? So all the other variables in the model. Okay, now this is a probabilistic model though, so I actually know that everything that I can find out about these guys, all right, what I can determine from these guys is going to kind of flow through this variable theta, right? So really all I have to do is kind of pick z1 given the probability of z1 given x1, y1, and the current value of theta. all right? Theta, I guess, was picked from this posterior somehow, okay? So I can pick Z1 first, all right? Then I go to the next variable here. That's this distribution, all right? So, so this basically, now I assume I know Z1 and Z2 and the prior. Okay, so I'm going to pick from the posterior. Okay, so that's another kind of another move, all right? Okay, yeah, this should be theta given these things, right? Sorry, all right. Then I continue, I pick Z2 given, you know, basically its Markov blanket. It's not its Markov blanket, but the things that it depends on, right? X2, Y2, right, and this guy, all right? Because all the influence of Z1 goes through theta, right? And then I keep going around the loop, okay? All right, so I just keep doing that, keep picking these things, all right? All right, so in a broad range of cases, this will actually converge to a sample from the true distribution. Okay, so if I'd done this correctly, it turned out that this probability was 60-40, okay, and you know, 6/10 of these things were class 1, 4/10 were class 2, and the particular ones that were class 1 and class 2 were, you know, arranged in some particular way. So in a broad range of cases, the sample I take will be something that's drawn from that distribution, where the sample is just basically, you know, the last 1,000 things that I've drawn in my loop. Okay. So among other things, I'll have a sample of the true theta. Okay. So this is a way of estimating theta. Okay. So here I want to learn theta. What I've come up with is a sample instead, but that's okay. All right. So why does this work? So the basic convergence claim, I mean, the math is not easy, but what it's saying is actually not very strong, right? What it's basically saying is that when you sample, okay, some variable from, you know, all the other variables in the model, given their particular values. So if it was the case that these guys were actually sampled from the true distribution, right, and then you sample x from the true conditional distribution, then you've just sampled x from the joint distribution, okay? So once you get to that distribution, then you stay there, okay? Once all the variables you have are things that are drawn from this true distribution, you'll stay in that point, so it's a fixed point, okay? So you tend to stay there if you ever get there. And how long does it take to get there? So there's a lot of math on this, but basically the story is this. So this is a graph that we've seen before. So imagine each one of these graphs, these points in the graph, is a point in our state space. So each one of these is a joint assignment to all the variables, all right? And these arcs basically means I can get from one assignment to another. So basically by doing a sampling move, I can get from here to here, okay? So, it will converge if that graph, eventually if that graph is connected, okay? And it will converge basically depending on how well connected that graph is. So here, you know, you could spend a lot of time sampling this blue part before you get to the red part. So going back and forth from blue to red is very hard. And it will take a long time for Gibbs sampling to converge in this setting. If you had a graph like this, it would be a lot faster. So the mixing time depends basically on the structure of the state space, specifically on the eigenvalues if you want to go back to spectral clustering. But this is really kind of theoretical interest because you never know what this looks like, okay? It's very hard to find out. What's more to the point is that Gibbs sampling, or certain variants of it, seem to work pretty well for the LDA model. All right, so the model we like using is actually a variant of Gibbs sampling called collapsed Gibbs sampling. All right, so that's the next thing I want to talk about. All right, so collapsed Gibbs sampling. Here's I blew this up to 3 examples now, just to make it a little bit more interesting. Okay, so here's the basic idea. What I'm going to do. So sampling this theta is actually kind of hard, okay? This is a continuous distribution. It's drawn from a prior. So I can find the map pretty easily, but actually sampling from the posterior is not immediately obvious how I want to do that. And in fact, it's not even clear that I have to do that. So what I can do instead is I can do the following. So I'm going to go around my loop and I'll pick this guy given all the other z's. So I'll pick this guy given z2 and z3, okay? So, and then what I basically have to do to make that work is, well, this theta is what I really want. Okay, that also depends on alpha. So I have to kind of throw that in there, okay? But I can look at this probability. So the form of that basically I have to marginalize out over theta, okay? But if I could do that, if I could sample from z1 given these guys and this guy, then that would be a sort of a correct sampling move, right? And since this is all the same, right? It's like if I do that for z1, I can certainly do it for z2 and z3. And I can do that in a loop, okay? So once again, this will converge to the true joint distribution. And then, of course, if I want to figure out what theta probably is, I can look at these z's. So theta is a distribution over these z's. If I can sort of see how many times each z has been drawn, I can guess what the parameters of theta are, okay? The trick here, then, is to pick z1 from this conditional distribution, given known values for z2 and z3, and alpha, the smoothing parameter. How do I pick z1? All right. So what does that distribution look like? Okay. So just to simplify, I just kind of took out the x's and y's. Gives me more room here. So it's a slightly simplified case. So this distribution is what we really care about. All right, because we kind of don't need the stuff underneath here for this exercise, right? All their influence is mediated through these z's. This actually is a pretty well-studied distribution, and it has a name. It's called the Dirichlet multinomial. It's basically, like I said, probability z1 equals this value given all these other guys. Okay, to do it, you have to marginalize out. So you have to integrate out over this theta. Okay, that looks like a bit of a chore. But it turns out to actually have a pretty kind of simple fixed form. So gamma here is actually a continuous generalization of factorial function. So gamma n is n minus 1 factorial. I'm not just like surprised here. That's factorial. Okay. So this is what the form of that is. That doesn't really help us all that much yet, but the sampling rule for it is really simple and easy. All right, and that's what makes this whole thing beautiful. So here's the notation. Okay, I've got k different values for the z's. So that's the number of topics. Okay, nk is the number of z's that have value k. All right, so all I really care is about the number of draws from each topic. Okay, so capital Z is this vector of random variables. Okay, capital Z minus I is that same vector, but I've taken out the ith one. Oh, there's a bug in there. This should be, let me fix this right now before I forget, because that's confusing. Wow, that's slow. Oh, how lame. All right. Anyway, you get the idea. This is supposed to be z sub I plus 1. So it's all these guys with the exception of z, exception of the ith one. All right. And this is the number of z's that have value k, excluding zi. Okay. So let's see, if this one has value 1, this one has value 1, and this one has value 1, okay, then to figure out what the value of z1 here would be here, it's like I add up those values, which would be 3, and I'd subtract this one. So that right answer would be 2. Okay, so this is all the number of zi's that have that value, excluding the ith one. Okay. So what's the sampling rule? So to figure out the probability that zi equals k, given all the other z's, all right, and alpha is basically just this. We have the smoothing for alpha. So this is the amount of pseudodata I have for alpha for the kth class, right? And then it's basically the number of values in these other z's that are assigned to class k, all right, excluding the ith one. All right, so that's really simple, okay? It's just that with a normalizer, okay? So in other words, to figure out what proportions to sample these guys, it's basically saying, I just count up the proportion of each class in all of these other ones, right? And I add this smoothing, okay? And that's the proportion that I should be sampling Zi at, okay? So if these are, if there's 100 of these Z's, and 50% of them are in class 1 and 50% of them are in class 13, I should be sampling about half class 1 and half class 13. Okay. So that's the sampling rule, and that's really simple, okay? So, so now I know how to do this sampling, okay? So that's pretty cool. But there's also some influence going in the other direction. So this isn't quite so obvious here. So we've got these words, all right, and we've got these Z's. It kind of looks like these words are kind of separating, but that's because I've got these arrows drawn in kind of a weird way for directed graphical models. So really, the kind of right picture is more like this. So I've got a Z here and a Z here, okay, and in between there are these betas, okay, and I've got some evidence here, the words, okay. So are these guys separate or not, right? Is this the value of this variable connected to this variable? Well, yeah, it kind of is, because this is kind of like the alarm situation. I saw an alarm, right? It's got two different common causes. So after I've seen that, observed that, these things are now dependent, right? And since these things are dependent, then these things are dependent. So that means that Z1 and Z2 are all dependent. Okay, so there's also some influence that kind of goes through these betas. All right, so the sampling is a little bit more complicated, but this is the full rule for sampling. Okay, so here's the notation again. K, we've got K different values, just numbers 1 through K for all these Z's. Okay, so this is the latent variable associated with document D at position I. Okay. This is basically, if I put a minus in front, that's all the Z's except for one of them, all right? This is basically the number of times that topic has occurred paired with that particular word, okay, the word that appears here, okay? This is the same thing but marginalizing out the word. So this is the number of Z's that have value K, all right? This is that same number excluding that one position. This is that same sum excluding that one position. This is, I guess, all the things from the same document, but excluding the ith position. All right. So here's the sampling rule. So to sample from this position of this document, all right, given that we had this particular word and we have alpha and beta should be here also, I guess. Actually, here I'm using eta, sorry, I apologize. This is etas and betas. I apologize for the switch in notation. Okay, so what's the sampling rule? So there's basically two things. One is the evidence kind of going above. This is what we looked at before. So this is basically the fraction of the time that Z has value K in the other latent variables associated with this one document, all right? So we're just looking at this one document, so the neighbors here are just all drawn from that same document because I kind of only care about things drawn from this distribution theta D, okay? So this is part of that story. The other part is the downstream evidence, okay? And here, since the downstream evidence is kind of surreptitiously linked through beta to all the other Z's, I have this, okay? So this is basically, if you work this out, this is the fraction of the time that W, the word W, is assigned to this constant value, this particular word W, in topic K, okay? So this is the fraction of time that you're in topic K in this document, according to the current sample. And then this is the fraction of time that, given you're in topic K, you've chosen word W, right? That's what these counts are, and this is just the smoothing, okay? So that's the sampling, all right? So The local sampling is very simple. Again, it's based, and it's also very intuitive, right? So there are basically two things. One is sort of a smooth estimate of how likely you are to draw that topic in this document. And this is a smooth estimate of how likely you are to draw that word given that you're in that topic. All right. So that's the basic idea. And there's actually some interesting dynamics to this. So once you have a word that's been assigned frequently to one topic, like say children, right, or budget, once that word has sort of like converged, so it's normally in the budget category, then that means that this probability is pretty high and the other probabilities are pretty low. So once a word has sort of converged and it's generally associated with one or a small number of topics, then you tend to put that same word back in the same topic. So one thing that kind of glues these clusters together is that you like to put the same words in the similar topics. So if you have two different occurrences of the word million, then there's a tendency for them to be assigned to the same latent variable. So that's this tendency. The other tendency is once you've assigned most of the words in a document to some topic or some mix of topics, you tend to assign the other words to that same topic. So the other thing that's happening is that words that tend to co-occur together will tend to get put in the same category. Okay, so there's another convergence here. So words, positions from the same document will tend to have, there's a tendency for that to have for them to have the same latent class, and that's determined by those mixing weights. Okay, so that's the basic idea. This is all the math. Let's go and talk about this in even more detail. So I kind of like getting down to like the level of an actual implementation. So here's an actual implementation. Disclaimer, this is a terribly slow implementation. You don't want to use this. This is just really for the purpose of exposition, but this maybe gives you an idea what you want to do. So a topic will be K, a document ID will be D, and a word ID will be W. So those are all going to be integers. Okay. X sub D sub J, okay, so this is like a two-dimensional array and a matrix if you want. It's basically the index of the jth word in document D. And this is the index of the latent topic for that word. Okay, I have another thing here, which is just the mapping the word index to a string that tells you what the word is for debugging. And then here's some further things we're going to keep. So we're going to keep track of the total number of words in the kth topic. Okay, the total number of words in topic K for document D, the total number of occurrences of word W in topic K. All right. And a total number of words in the corpus. All right. So these are a bunch of counters I'm going to keep. These are these things that were summations in the math. All right. So let's start out. So I have this little sparse thing called a topic counter, but don't worry about this. This is basically just initializing these guys to zeros. All right. This is initializing all the z's to -1 and just allocating that space. All right, and now what I'm doing here is probably a sparse matrix would be a much more efficient way of doing this. For every D, for every document, I'm going to go through here, okay, and then for every position in that document, I'm going to go through that and look at that position, and I'll pick a random topic, okay. All right, so first I look at the word, okay, I'm just looking it up. All right, I pick a random topic, just uniformly at random from 0 to K-1. All right, and I set that latent variable to be in that topic, and now I've got to like update my counter. So I've got one more. That topic has occurred one more time in this document. All right, that word has been associated one more time with that topic. Okay. I guess K has been used one more time. So that the total number of times that topic's been assigned has been, it should also get incremented. And then these are the smoothing parameters that I'm going to use. Okay. So this is basically just putting in an initial random set of assignments. All right. So then here's the Gibbs sampling algorithm. Okay, so I'm going to go through a fixed number of iterations. So for LDA, something like 30 to 50 would be a reasonable guess. So it probably won't converge in 5 or 10. It probably won't take as long as 200 or 300. So around 50 is sort of a good guess. So we're going to iterate over the corpus a number of times. And again, we're going to loop over every document, and we're going to loop over every position. All right, I'm going to pick a new value for the topic. Okay, and then I'm going to update my counters. Okay, so let's talk about these steps. Okay, so updating the counters basically is the following. I've got the old category. That's this one. That's the new category that I just sampled. Okay, that's the position. All right, so if I happen to choose the same topic, I don't need to do anything. Otherwise, let's look up the word. Okay, and now we're just going to do a bunch of counter updates. And then finally, I'm going to store that new topic. Okay, all right. So that's basically the bookkeeping I need to do to switch classes and also keep these running counts going. All right, so that's pretty easy. So the last thing is this resample step. Okay, so here's where I draw from the distribution. Okay, and this is all the code. Okay, all right, that's all the code for the resampling. Okay, so so let's figure out the probability of being in topic K. All right, so this is the probability that the latent variable in document D position J has value K, given all the other things. Okay, so let's look up the word. All right, so I'm going to go through each of the topics and compute this. So I've got to adjust all my counts, okay, because the counts are all for all the other Z's except for this one, right? So I'll first figure out whether this particular Z has this particular value of K, right? So that's going to be a number. That's going to be my correction, okay? So for the Kth topic, I've got to correct things by subtracting 1. For all the other topics, I can leave things alone. All right, so I'm going to look basically at something that's the probability of two things, upstream and downstream probability. So the upstream probability, it's basically the top of that fraction. Okay, so it's the probability, it's the count, the number of times that that topic appears, topic K appears in that document. All right, and here's my little correction term. So also one of those in the sum. And there's the smoothing, okay? And I'm not going to put in the normal. Then this is the probability of picking the word, okay? So there's sort of like, here we do need to normalize. So this is the number of, the fraction of times we have that word in that topic. Again, corrected for this by removing the count for this position, plus the smoothing, all right? And this is the smoothing we get on the bottom. We're multiplying that by the total number of words. The denominator here is basically, so this is the probability of drawing the word given that topic. So this is the total number of times we've drawn that topic. This is the number of times we've drawn that word in that topic. And we've got the corrections and, of course, the smoothing. All right. So that's another thing. I'm going to multiply those out. Okay. And kind of as I go along, I'm going to compute the normalizer. Okay. No, let me go back here. I thought I had a nice little picture of what's going on, but I don't. So now finally I want to pick. I could actually, and actually probably I should just to make this clearer and simpler, I could go through and take all these PKs and divide them by the normalizer. For some reason I decided to get fancy here. So I pick a number between 0 and 1, and then I go through and kind of as I'm going through, I divide PK by the normalizer, okay? And basically I'm just trying to see whether the sum of all the PK so far is large enough that this is in that right value. Let me draw that picture. Let's see if I can find that picture. I think I have that picture somewhere. Yeah, here we go. Here's a picture. Right. So these are the probabilities of being in each category that I've computed here. I really need to scale these to unit height, but I'm going to do that in the process of this loop. Okay. I pick some random value, and I want to find out what interval it's in. So I'm basically going to go through here, okay, and the first time my sum is larger than the random variable, or the random value is smaller than the sum, then I'm going to say, okay, that's where I ended up. That's my topic. So if this is where I land up, I'll say that's topic 3. Okay. So this is the whole resampling process. I have to compute these probabilities, and unfortunately, I only get to use them once. And then I draw a random point in that according to that distribution. All right. This is actually where you spend all your time in LDA. Okay. All your time spent sampling. All right. So what you learn at the end of the day, basically all you've got is these counters, okay? So, but that's enough, okay? At the end of the day, if you want to find out what's the probability of a word under a topic, you can just do this little computation here. So you have the total number of words assigned to that topic by their latent variables. We know how many times that was word W, so that's the smooth probability, okay? So, so that's the weight of the word under a topic. So that's how we can get my nice list of what are the most important words of each topic. If we want to figure out how a document is mixed, say I want to use those weights to do features to run SVD or SVM like we did in the, and I showed a couple slides back. I use the same similar set of counters, so I basically look at the number of times that topic has been assigned. I don't actually have the total number of assignments within that, the total number of times that any topic has been assigned for a document. I guess this is also the length of the document, so maybe I don't really need that. Okay, but again, we've got the smoothing. So this is basically the fraction of a document that's been assigned to topic K, so topic K. All right, so these phi's right here are the word probabilities, so these are the multinomials, and these thetas right here are the document mixing. So that's the basic idea. In the interest of time, I'm not going to go through these last few slides. It's basically the same thing. I'm just putting like sort of a mathematical gloss on this. So this is more of a math notation, sort of lining it up with the Python. So I guess the nice thing here is, or one thing that might be worth looking at here is this formula right here. This is where it gets a little bit messy. Okay, so this is this first probability here, and this is that second probability BK, and this is that correction term. Okay. So I'm actually going to stop here. I'm going to take there's in the slides. Those of you who are at home, in the slides, I also ambitiously assumed I was going to talk about parallelizing LDA, but I think I'm going to leave that for next week. So Thursday, no class, just so you guys know. Next Tuesday, I'm going to take a break from LDA. I'm going to talk about this architectural idea called parameter servers. And then Thursday, I'm going to go back to LDA, and we'll talk about a whole bunch of fancy big data learning tricks to speed it up. So that's the next few days. See you guys next week. Happy Thanksgiving.